Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to give you another example related to getting the information out of the first derivative and the second derivative and use them to visualize the graph of the given function. Well, in this question, you have a function that is given as such. It looks quite simple, but looks can be deceiving. You've got to try it on your own first and see how tedious it can be, especially because we've got powers in terms of fractional number here. So just be careful on that. Well, without and I think it might take a considerable time to get it done, to get the first derivative and the second derivative. Therefore, I'm going to omit that in this video. I'm just going to write down the answers to the first derivative and the second derivative. So you can go on and try to verify it on your own, okay? So this is the answer to the first derivative, which is 4 minus x over x, the power is 1 over 3, 6 minus x, and the power here is 2 over 3. And for the second derivative, the answer is negative 8. And at the bottom, we have x 4 over 3, 6 minus x, 5 over 3. Okay. Make sure that you get all these answers as seen on this video. And if you can't get the answers, please let me know and I will show you how to get these answers. All right, now assuming that everything is going all right, we are now going to focus on the result of our first derivative here, and we're going to start off by finding what's the critical points. Okay, so according to what you have seen in the previous slide, where is it? This one. Okay, so this is the slide. The critical number is the number such that when you plug into the first derivative, the result is going to be 0. The result of the first derivative is 0, or the result does not exist. Okay, the function does not exist. And with that in mind, we are going to go back to our example here, and I hope that you can see when x is equal to 4, the result here is going to be 0. Now, this result will not exist if you have x here equals to 0, because then the denominator becomes 0, the whole denominator becomes 0, and this function becomes undefined or does not exist. And this function also will not exist if x here is equal to 6, because then 6 minus 6 is going to be 0. So 0 multiplied with this guy over here, the whole denominator is going to be 0, and so the function does not exist. So these are the points, the critical points, where this one, f prime c, is going to be 0 when you substitute 4 into this function. And this one is the condition where when you substitute, you will get the answer is this one will not exist. Okay. So now let me just highlight this. These are the critical points. Now once you have obtained the critical points, our job is to divide the domain of x into proper intervals, and the intervals here are based on these critical points, these numbers. Okay, so my next step is to construct a simple table which you have seen done in the previous video. So interval, and then over here the first one is considering x less than 0. Next x between 0 and 4. Okay, between 0 and 4. Next are x between 4 and 6, and finally x greater than 6. So those are the intervals based on these critical points. Next, we are going to study how the first derivative behaves, and therefore we need to consider the factors related to this first derivative. So this is the first factor, this is the second factor, and the third factor. So we're going to consider that and see how does this affect the sign of the first derivative, and how this then in turn affects the behavior of function fx. Okay, so the first factor is 4 minus x. Next is x 1 over 3. Next is 6 minus x. 2 over 3, I'm going to write down in terms of 1 over 3 and square, so that you can see it clearly after this. Okay, so 1 over 3 and then squared. Next f prime x, this is the behavior of f prime x, and finally we have the behavior of fx. Okay, so when x is less than 0, the value that we have over here is going to be positive, because negative and x is also negative. Negative and negative will become positive, so you get positive sign for that. And for this one, because x is less than 0, which is taking a negative value, now a negative value and then finding the power of 1 over 3, so that will be going to be negative. For this one, similarly we have negative with a negative value, so the inside here is going to be positive, so the overall expression here is going to be positive. Now multiply the sign, consider the multiplication of the sign here, so you will get the final answer is negative. And therefore we can say that this function is decreasing on the interval of negative infinity and 0, not including 0, and that's why we're using this round bracket. So for the second interval here, following the idea in the same manner, you will see that this one is going to be positive. This one is also positive. This one is going to be positive, because 6 minus a number that is less than itself is positive, so the whole expression is positive. Therefore f prime x is positive, so we say that fx is increasing on the interval of 0 and 4. Next, between 4 and 6, well, between 4 and 6, this is going to be negative. This is going to be positive, because x is a positive value. For this one, x is a positive value and x is always smaller than 6, therefore the expression inside here is positive, and the whole thing here becomes positive, and this becomes negative. Negative times positive is negative, negative times positive is negative, so that's why the result is negative. So we say that fx is decreasing on the interval 4 and 6. Now finally, for x greater than 6, for x greater than 6, this is going to be negative. Now x is positive value, x greater than 6, x is positive value, so this is going to be positive. Now 6 minus a number, x is now greater than 6. 6 minus a number that is greater than that, this is going to be negative. When you have 1 over 3, the result here is also going to be negative, but then you have the number squared, so then the whole thing becomes positive. Okay, finally you have the final result, negative sign. Okay, and because of this negative sign, we say that fx is decreasing on the interval 6 and infinity. Okay, now we have managed to visualize the behavior of fx. Now based on the first derivative test, you can also determine whether you have the local maximum or local minimum. Okay, so that's what we're going to do next. We're going to determine the point of local max or local minimum. Now if you see point 0 over here, so now we talk about point 0, x equals to 0. So this is yeah, I can sketch it over here. So this, you can imagine this being point 0. When x is less than 0, you can see that it is decreasing. So you can imagine a function going downwards. And then when x greater than 0, it is increasing. So after 0, it is increasing. So you can imagine there must be the point of local minimum. So we can say that local minimum is x equals to 0. And when x is equal to 0, you can find what is the value of fx. So you just substitute x equals to 0 in this function. Therefore, you can see that fx is going to be equal to 0 as well. That is local minimum. Now, if you go on and study point x equals to 4, so for x equals to 4, so I'm just going to simply sketch this simple diagram. So x equals to 4. So when x is being less than 4, the graph is increasing. So you can imagine that it is increasing, okay, increasing on the interval between 0 and 4. And then when x greater than 4, immediately after x passes 4, it is decreasing. So that means it reached a point at 4 and then it's going to decrease. So based on this idea, you can see that at point x equals to 4, there must be a local maximum point. So I'm going to write down the local maximum point is when x equals to 4, and you can find what is the value of y, or what is the value of fx, by substituting 4 into this function. So when x equals to 4 is substituted into this function, you will get that the answer is about 2, 5 over 3, or this is approximately around 3.175. Okay, it's about that value. Now, how about x equals to 6? Now, for x equals to 6, okay, I'm going to just sketch this. So this is 6. You can see that for x equals to 6, for x being less than 6, it is decreasing. So you can imagine the graph going downwards. And then for x greater than 6 also, the graph is also decreasing. So it just continue decreasing. Therefore, clearly there is no local minimum or local maximum. So what we can say is for x equals to 6, there's nothing that you can say about that. No local max or minimum. Alright, so that is all the information that you can obtain from looking at the result of the first derivative. But these results are not enough to sketch the graph of the function, and so we are going to move on to study the second derivative. Okay, I'm just going to erase some part of this slide. Okay, and we are going to study the second derivative. Okay, just give me a moment to start to erase all this. Okay, we're almost there. Just hang on a bit. Alright, now we are going to study the second derivative. So the second derivative is given here. This is the second derivative. And based on this second derivative, I hope that you can see the points of interest will be when x is equal to 0, because why? When x is 0, so when this becomes 0, the whole thing here will be undefined. The whole thing here will become 0, and so this second derivative will be undefined or does not exist. And similarly, when x here is 6, when x is 6, you can see that the whole thing becomes 0, and so the denominator will become 0, and the second derivative is going to be undefined. So these two are the points of interest where we can again construct the domain of x into this into some intervals that are based on these points that you have over here. Okay, so I'm going to construct a table. So interval. So the interval will take into consideration these 2 points here. Okay, so the first one is x less than 0. Next is 0 and x and 6. So x between 0 and 6. And finally is x greater than 6. Okay. Next, in order to understand the behavior of the second derivative, we are going to consider the factors that we have here. So maybe the first one is -8. This one is x 4 over 3. And this one is the term that you have over here. So now I'm just going to write down -8. X 4 over 3. Or maybe what I can do is I can write down in terms of like this. I can write down in terms of x 1 over 3 and then power 4 outside that. It's the same thing. And then 6 minus x, so 1 over 3, and outside is 5. Okay, and then we will have the behavior of the second derivative. So finally, based on that, we can see whether the graph is concave upward or downward. So we are talking about the concavity of fx. Okay, next, let's get on with it. When x is less than 0, doesn't matter what value of x, it doesn't have anything to do with x, so always the sign here is going to be negative. Okay, now for this one, when x is less than 0, so that means x here is negative. When you have 1 over 3, your power is 1 over 3, the result is going to be negative. But then you have an even power outside here, which is 4, so the whole result will be positive. Now for this one, when x between 0 and 6, x is positive, so the whole thing just becomes positive. When x greater than 6, again this is positive value, so the whole expression here becomes positive. Now for this one, when x less than 0, that means x is negative, so negative and negative value, it will become positive, so the whole expression here is positive. The power is 1 over 3, which is going to be positive as well, and then we have an outside power here, which is 5, so the whole thing will have a positive look. Between 0 and 6, again, between 0 and 6, everything here is positive, so the whole expression is positive. Now when x greater than 6, 6 minus a number that is greater than 6 will be negative. So 6 minus a value that is greater than 6, the value here is going to be negative. Negative value with 1 over 3, the power is 1 over 3, the result is going to be negative. And then you have power of odd number, so the whole thing is going to be negative. Now what we can do next is we are going to consider multiplying the sign here. So you can imagine having the sign negative multiply with a positive value. So negative value with positive value will be negative. Negative and positive will be negative. So we get negative, negative, positive, negative, negative, positive will be negative. negative, positive, negative, negative, negative is going to be positive. So based on this, we can say the concavity of fx is going to be downward for the interval negative infinity and 0, and then it is going to be also downward for the interval between 0 and 6, and it's going to be upward for the interval 6 and infinity. Now based on this information, we can go on and try and sketch the graph. I have this very limited space here. I'm just going to use this space. So let us try and do this. Okay, this is just a rough sketch. You can go on and try and do it better. So what I have here is I have this one, this line. Okay, I'm running out of battery. Just wait for a second. Okay, right. So let's say that this is my x-axis, okay, and then over here is I have my fx. Now I'm going to sketch the points. Here we have x0 until 4, so and we also have at this point here. Okay, so if I consider this point here is doesn't change, so it doesn't change, it is downward and downward, so it is not point of inflection. But for point x equals to 6, is the point of inflection, because the concavity of x changes from downward to upward. So there is another point to be considered, which is point of inflection. So point of inflection is when x equals to 6. So when x equals to 6, you can plug into this original function and get the value of fx. So when x is equal to 6, y is going to be, or fx is going to be equal to 0. So we are going to consider all these points in order to sketch the graph, and also the concavity of fx, and also the previous table that you have constructed, which is related to the increasing and decreasing intervals. Okay, so okay, let's go back to this graph here. So this is point 0, maybe 1, 2, 3, 4, 5, 6, something like that. And now we are going to start by plotting the important points. So when x0, fx is 0, so this is 1 point, and then x is 4, this is about 3.1, so x is 4, this is about 3.1. Okay, let me just consider that. So this is 1, 2, 3, so maybe somewhere here. So we have 4, and this is about that point, 3.1. Next, for point of inflection, x is 6, fx is 0, so this is going to be at this point. So we have managed to get these 3 important points here. And we know that previously when x is less than 0, the interval is decreasing and concave downward. So basically it is increasing and concave downward. That means it's in this direction. Okay, now why is that so? Because you can see that if I select, let's say, a point here, I can see that the tangent line is going to be above the line, the curve, and therefore we say that this is concave downward. So you have to if you don't remember, you have to recall the definition of concave downward and concave upward. So now we can imagine the graph is decreasing, but in a concave downward manner, so it might be something like this, something like this. Next, for x between 0 and 4, you can see that the graph is increasing. So recall that between 0 and 4, the graph is increasing. Okay, and between that interval also, you can see that it is also concave downward. So what does it mean is that it is going in this direction, increasing, but going up in this manner. And again, why is it like this? Because when you see, if I choose, let's say, this point over here, I can see that if I construct the tangent, the original curve is below the tangent line, and therefore this is a definition of concave downward. So we are going to sketch, right? So maybe it's something like that. Yeah, so that's the graph between 0 and 4. And then between 4 and 6, okay, between 4 and 6, you have to refer to the another table, the previous table. Between 4 and 6, the graph is decreasing, and between that interval also, the graph is decreasing in the manner of concave downward. So decreasing but concave downward, so we are talking about this graph decreasing and also concave downward. So it is going to be something like this. Okay, so like this. Okay, next, at point 6, when x is greater than 6, the graph is decreasing, and it is decreasing in the manner, the concavity is concave upward. So decreasing but concave outward, that means it is in this manner, decreasing but concave upward. Now why is it such? Well, if you pick one point here, so this is one point, the tangent line is going to be constructed like this, and you can see that the curve here is above the tangent line, and therefore that is the definition of concave upward. So at that point, again, it's going to be decreasing in this manner. Yeah, so something like that. So that's how this graph is going to look like. And you can see that at this point here, this is the point where the function f prime x is doesn't exist, or is not defined, because there is a sudden or abrupt changes. And at this point, the reason why it is not differentiable is because you have a vertical tangent over here. So if you don't remember why is it not differentiable, you have to refer back to the previous lecture note about the situations where fx is not differentiable. Okay, right, I think that's all from me for now. Thank you very much for watching, and I'll see you in the next video.